is Wen-Han from National University of Singapore. And today I'm going to tell you about sub-bath cooling in continuous variable system. Let me start by explaining what cooling is. So as you can see throughout the conference, the nice analogy would be the occupation numbers you have on the first day and the last day. And I will use this. So cooling basically means reducing the mean excitation. And this also corresponds to lowering the entropy and the temperature of the system. Okay, and then now let's take a step back to the classical thermodynamics. So what I mean by sub-bath cooling is basically mean that this operation should lower your system temperature beyond the environment temperatures. And the non-trivial condition would be when your environment is hotter, then in this situation you actually need an external work to pump the entropy out of the system. And this is nothing but we have learned in our undergrad thermodynamics, reverse Carnot cycle. And yep, now we are going to quantum. So a nice analogy would be we replace the system with a quantum density operators. And now the operations, the cooling operation would correspond to a quantum channel. And this quantum channel actually takes external works from the lasers. And the only role it needs to do is to pump the entropy out of the system to the ancillary system. And the ancillary system, we call this a machine. And for this cooling protocol, if we want to do this iteratively, we need to reset the machine. So actually, we also need a bath to thermalize with the machine for the resetting process. And a systematic way of looking at this would be this protocol known as the heat bath algorithmic cooling. So in these protocols, we have two steps. The first step is recharging, and the second step is thermalizing. The only difference would be in recharging process, the unitary need not to be energy preserving. And of course, you could do this iteratively, and this is what we call as a collisional models. So within this framework, we want to answer two questions, basically. The first one would be, what is the cooling limit? When can we do cooling? And the second one would be, what is the cooling efficiency under finite resource? So, and the setting that we want to answer this question would be in the framework of continuous variable system. In this framework, we assume that all of the input state is all Gaussian state and all of the allow operations is Gaussian operations. And before I move on, let me briefly tell you about what are the known results in CV cooling. The first one would be no cooling for single mode thermal operations. So in this work, they're basically saying that the best you could do with single mode thermal operation would be to maintain your current excitations, or you can just swap it with the system with lower excitations. Now going to the second part. The second part is about efficient cooling with finite resource. So let me get to the first part, efficient cooling. So what I mean by efficient cooling is basically no extra heat dissipation. And the way we quantify heat dissipation is coming from the Landauer bounds. The intuitive way of understanding this would be, during the resetting process, you need to reset the ancillary system. But then if now your ancillary system is correlated with your system, it actually generates heat. Or somehow your cooling protocols actually changes your marginal state after the cooling operation. This also generates heat. And when you add them up together, this is how I quantify the extra heat dissipation. And the efficient cooling would mean you actually want to minimize over this heat dissipation. Now let's get to the second part, which is the finite resource. So I quantify finite resource through the energy control complexities and time. So you look at the cooling protocols in terms of the circuit. By energy, I mean the gap of the machine or ancillary they use in the system. Control complexity would mean like how complicated is your gates? Like, do you use non-linearities? And time will refers to how many steps of collision you need to cool down the system. Okay. So the open problem would be, for the first case, the cooling limit, we actually don't know whether these results extend beyond single mode and beyond Gaussian thermal operations. And we also don't know whether swap is optimal in these conditions. And for the second part, most of the work has been done for discrete variable models, and we would like to extend this to continuous variable models. Okay, so let's go into the main content. So now, first part is about cooling limits. So in this setting, we assume that the temperature of the machine and the system, they are all the same to begin with. And now we'd like to know, when can we do cooling in such a setting? So when we look closely to the operation that we can have, the configuration that we can have would be the gap of the system for each of the ancillary, and also what kind of Gaussian operation you can do in the middle. And I'll just show you the results. It's actually quite simple. So we show that it is actually, you can't do cooling if the gap of your ancillary system or the machine is smaller or equal to the systems. The only way you could do this would be when the gap of the machine is larger. And the cooling limit, or the temperature that you can reach with Gaussian operations, is given by this. And lambda would be the ratios between the machine gap and the system gap. And we also proved that the most optimal operations is swap operations. Now, going back to collisional models, so what we need to do here is basically do the next operation, but then for the next operation, you actually need an energy gap with a larger gap, so on and so forth. And yep, this would conclude the recharging process for the CV heat bath algorithmic cooling. And the recharging process would be simply thermalizing with the bath to reset the ancillary system. So you might wonder, why don't we just do the swap in one go? And that's because of heat dissipation. So like I said, you need to actually make sure that your ancillary system, you want to perturb them as least as possible. So when you have collisional model, it would mean that when you do this iteratively, this thermal state must be roughly the same. But then we don't know. These are the three parameters that you could optimize over. But then we don't know whether when you do this collisional model over time, is it like linear or some nonlinear functions? So we show that we have analytical results and a numerical simulation for this for n equals to 5, and we get like the optimal energy gap for the minimum heat dissipation. And the graph on the right-hand side would be when you plug in all of these optimal parameters. This is the heat dissipation that you get. And we are comparing with the analytical one, would be the one where we take the number of collisions to infinity, and we got some continuous curve. And then we sample 5 points to compare the heat dissipation there. Okay. Yeah, so if you don't understand the previous slide, that's fine. I want you to take home with the message of why Gaussian cooling is not enough. Now I'm comparing the case where you have degenerate qubit scenario and degenerate CV states. So you can take one state as your system and then two states as the machine. A nice way of looking at this would be to combine the machine together. And if you're coming from qubit cooling background, you can immediately know that you could do cooling by three-body swap, and this is possible. But then when you look at CV model, if you want to do the same thing, it is actually not allowed by Gaussian operations, because as we showed that previously, swap is the most optimal operation that you can do. And swap, the physical interpretation would be nothing but the beam splitting operation. And this is strictly two-body interaction, which means you can only exchange one excitation at one time. And in order to do something like a three-body swap, you actually need nonlinearities or non-Gaussian operation to do this. And that brings us to the next word about non-Gaussian cooling. So the only difference here would be we change the recharging routine to something with nonlinearity. So we take AB to the power of P, and P can be larger than 1. If it is 1, then you're recovering the swap operation. But if you go higher, it actually induces more non-Gaussianity to your protocols. And of course, we do the collisional models again, and we find that this is the result of how the mean excitations evolve as you do the collisional models. And the Gaussian cooling limit is indicated by this box. As you can see that when P equals to 2 and 3, you can actually go much lower than the Gaussian limits, and it's actually converged much faster. Yeah, so this would be my third result about the Gaussian, beyond Gaussian cooling limit. So a quick recap will show that if you only have Gaussian operation, even the most optimal one like the swap, as long as your gap of your machine is smaller or equals to the system, it is not possible for you to do cooling. But then in the very same system, if you now have, you can tap into the powers of non-Gaussianities, you can actually have access to the higher excitation, because now you can exchange one excitation with P excitations, and this makes cooling possible. And the cooling limit is given by that thing, okay? Yeah. So a quick summary. We show the necessary and sufficient condition for Gaussian cooling and non-Gaussian cooling. Yeah, also show the analytical and numerical studies for the optimal heat dissipations and for Gaussian cooling. And then for the non-Gaussian cooling heat dissipation, we'll leave that for future work. Yeah, this is quite fast. Okay, so this work is done in collaboration with Shandong University, Xueyuan, which is our collaborators in Singapore. And if you are interested in this work in the more mathematical detail, you could check out our paper. Yeah, thanks.
Okay. Okay, great, thanks. So, questions? It's been a long day, but I guess, go ahead, Fede. Yeah, the microphones are tired.
Hello. Very cool work. So I guess, can you imagine using this as a witness of non-Gaussianity? Would it make sense?
We actually thought about that.
So also non-Gaussianities in general are a resource, even for example, computational advantage. And I wonder if there are similar limitations in cooling qubits. As in if you restrict, for example, to Clifford or to stabilizers operation, maybe you cannot cool enough.
You could think of like cooling as lowering mean excitation, right? So for mean excitation in series models, it's actually composed of the contribution from the first moment and second moment. And then, at least for Gaussian operation, if you decompose it into squeezing or displacement, it affects only either the first contribution or the second moment contributions. But now if you include non-Gaussianities, it can changes two moments at the same time. And we think if you want to do non-Gaussianity witness is possible, but then I don't think it's sufficient to use it as at least for the energy metric, to use it as like a non-Gaussianity measure.
And how do you simulate non-Gaussianity?
Oh, it's the collisional models where we take those, let me see. Let's go back. So it's basically, it's all coming from this multi-excitation Hamiltonian, where we are using collision models, and in short time limit in each collision, you actually do this, you exchange one excitation with multiple excitation, and then you do this the collisional models with.
But how do you characterize the state or the quantities? If it's an like it's a non-Gaussian state, it can be arbitrarily complex with infinite many degrees of freedom. Do you put cutoff somewhere? Do you cut off the Fox basis? Do you take finite energy?
Oh, you mean like the numerical simulation part?
You don't. Oh, it's all analytical.
Yes, it's all analytical.
Okay, cool. I want to know how.
Yeah. It's a weak perturbations, basically, because it gets
Weak theorem.
Yeah.
Okay.
You can get simplification from there.
Any other questions? If not, I have a quick question. So, I know two-level systems much better than than the other systems. So, in your two-level system example, I think I could sit down for half an hour and invent some quantum circuit or something with some gate operations that would do what you want to do, which is to move, is to do the swap from the 2 qubits excited into the other one. But I don't have any experience with these more continuous variable things, so is it easy to make a Hamiltonian of this kind with this A, with the B to the power of P? Or did you think about scenarios where that would be easy to implement experimentally?
For sure, as for higher P's, it's generally more challenging to implement in experiment. But then
for P equals 2, for example, yeah.
2, I
so
think it's
something like this.
feasible. It's like the SPDC stuff. And I think in CQT, where I've also worked by the trap ion group, we'll actually implement something similar. Yeah.
Okay, very nice. Thank you. Okay, so let's